Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Enrico Belmonte.
Hey, Enrico. Hey, we were chatting, was it last week? We were chatting with a couple other folks about a variety of topics, and you had mentioned, and it was in context to testing, that, evaluating components and evaluating subsystems and stuff is good, yet it's not complete product at that point. And there's a lot going on. And you were talking about white appliances, and there's fluids and heaters and spinning things, and it's all kinds of weird stuff going on. And you mentioned that it was a complex product and that we needed to put it all together and test it adequately. And to some extent, I agree. We had different discussion about that topic, whether to test it as complete or not. But it dawned on me that, SpaceX makes rockets, and it's a complex product. A vehicle, like a car, is a complex product. A satellite, depending on like the Hubble Space Telescope. And I would call that complex. But
Yeah.
I also worked on a pen, a fountain pen kind of device for handwriting, right? And it's one of the most complex products that I've ever seen. It's simple in not a lot of parts, but if you don't get it right, you're going to have ink all over the place. And if you don't have it right in the other direction, you can't write at all. So it's complex in its precision, kind of thing. So I think that term gets misused in product development a bit. And what do you think?
Yeah, so that's a good topic. So as you know, I worked on brake system and on home appliances and other sectors. And I think we need to start with distinguishing between complex and complicated, right?
Mm-hmm.
And for me, complex is related to how many surprises you can get, right? During the development, right?
And to some extent, that relates to how many components and subsystems you have in a product.
Yeah, but I would say this is complicated. How many components? So if you have a lot of components connected to each other with a lot of interfaces, you have a complicated in terms of how many things, how many rings in the chain I have, right?
Right.
But
Okay.
yeah, what I'm trying to say is that the product might not be so complex, but the level of engineering you are spending for developing it is not sufficient to cover all the surprises that you can get afterwards. This is a little bit, it's not, it's kind of trade-off. I think the example you made with SpaceX is definitely interesting because they definitely cannot. They tested, right? They tested. They tested, and the sample, let's say, sample size cannot be so big, right?
Right.
And they need extremely good engineering, right? For producing what they are doing, right? But complex to me, it means, and if I need to be honest, is like, okay, we have done proper engineering for most of the components or for most of the scenarios, but we still have, or we might expect some surprises, when putting everything together, and therefore we need this level of testing at system level for covering whatever we might missed or we might forgot before.
Well, yeah, a variant of what you're talking about is in my history. I worked with desktop computers at one point, and one of the people I worked with in that team worked, I was at corporate and they were in that division and they were saying, how do you handle all the various permutations? And I said, what do you mean? He says, well, we design the chassis and the look of it
Mm.
and the basic BIOS and a couple other pieces of it, specify the chips and a few other things. But we have a motherboard that can have an Intel chip or an AMD chip on it. It can have memory that the user can put in themselves. So it could be from a dozen different vendors. Um, the hard drives can be selected and changed by the owner of the system. And there's 8 or 9 key vendors out there that can do it. And on and on and on. All of the major systems, including the keyboard and mouse, different adaptions. And it was a classic Intel-based machine where there's a basic structure there, but you could add whatever kind of mouse or trackpad or rollerball or whatever you want to it, and it has to work. And they're saying we did the math, and if we just built one unit with each one being a unique combination of what's possible, we'd have to make a couple 100,000 different units. He says, and
Yeah.
then test them, and then those are all samples of one. And to to me, that's similar to, well, there's going to be surprises. We're meeting the standard, but if that trackball vendor doesn't exactly meet the standard the way we interpreted it, we're going to be surprised, or our customer's going to be surprised.
But you're talking about function, right? Not about reliability
Well, if the customer can't use their trackpad in their system, it's a failure from their point of view. It's not working.
yeah.
It should work. It's
Yeah.
not working. It's your fault. This is your name's on their computer.
Yep. Yeah. But yet, just to understand, is like a zero time failure, right? So we say, hey, my trackpad is not working right from the beginning.
Yeah.
We have like, yeah. So
But I mean, it also goes with memory. It could be that the memory doesn't clear correctly so that it
yeah,
over, it doesn't clean caches or do stuff like that. There's all kinds of ways that these permutations then show themselves in the interfaces a lot of times. And so
yeah,
it gets to the point where you want it to work, but you don't want the requirement, the specifications to be so broad that nothing works.
yeah,
And I think to me, the complex involves, I agree with you, with surprises. And there's these things, what they called it was white space. It's that this power supply doesn't like working with that memory.
yeah.
And we don't know why, but they don't. If we change either one of them, it works fine.
I think you touched two important topics here. So, of course, when we design for reliability, we design against the damage mechanism, right? So,
Mhm.
if you know the damage mechanism and you do not know whether uh, the damage mechanism for different vendors, for example, occur in a similar time,
Mhm.
you might get some surprises in terms of, hey, the new vendor, the failure, the failure rate of the new vendor components is like double, twice as the previous one.
Yep.
Yeah. So, and that is a kind of surprise, that is in many cases hard to read before, because you do not get data, or you don't have time to characterize fully in terms of reliability all the components, all the suppliers,
Well, it's
it
even
might be.
suppliers change a step in their
Yeah,
process, and the
yeah,
polymers don't behave exactly the same way.
yeah, and you have some control on the first supplier, let's say sub-assembly supplier, but you do not have any control on the sub assembly supplier or component supplier, this kind of things.
Yeah.
The other kind of surprise, I think, is related to the occurrence of new damage mechanisms, right? This is quite a nightmare. Yeah.
Oh, yeah. Yeah. No, I agree with you. It's
Yeah.
yeah. There's something that because SpaceX and large satellite systems and all kinds of units connect with the engineering, and I don't believe the engineers at NASA are better or any worse than the engineers at Bosch or at Microsoft. Well, I don't know about Microsoft. I work with them, but uh, that's a joke. It's a joke.
Yeah.
Good people there. But the idea is that the level of scrutiny and the budget and the timeline is bigger for higher risk single shot type stuff. And you know, a big complicated massive rocket, we're not going to get 30 of them just to test to see if they work or not. We're going to get one in only parts of it. So the engineering goes up a little bit, but I've never found that engineering keep the space and time and expertise scales linearly with the risk.
Mm.
It's still a lot of trade-offs, a lot of unknowns, a lot of uncertainty. You know, you got more time, but you're digging deeper. You're going into more interfaces, you're going into more problems. So the the complex systems tend to get more engineering time devoted to them, but I often have found that it's not sufficient. And even
Yeah.
you would think they would have all the time in the world, but hey, you still got to ship it. You got to launch it.
Yeah, and there's another important point, I think. So, as reliability engineers, we always focus on damage mechanisms, right? So we
Hmm.
say, okay, the component A should fail due to fatigue, the component B due to wear, the component C due to creep, and so on.
I would add to that system because you're talking about, you know, kind of end of life type mechanisms where they should,
Yeah,
you know, occur. If they occur earlier, that's a problem. But there's also problems with a vendor doesn't control their cutting, so the parts aren't in spec or they're not
yeah,
consistently on target, right? Or change in a process that affects the ability of the coating to adhere anymore. And they don't tell you about it. There's some of those that become latent defects, like depaneling a circuit board. If you don't do that correctly, you can break components and vias and
yeah,
chases. So and sometimes they're in a spot where, like, you break a small capacitor, it may not be detectable until it thermal cycles, say, 500 times. And then it fails, and now you lose that board. So
yeah.
there's the failure mechanisms is not just the long-term stuff that we typically think of with accelerated life testing. There's also all of those latent defect things and issues that show up during the assembly and manufacturing processes and transportation and so on.
Yeah, and that is well explained by the bottom curve, right? Bottom
Yeah, yeah.
curve concept that we might need to have a podcast on that. I think it would be really beneficial or interesting, like
Oh, yeah.
for discussion. But what I was saying that, like, I agree with you. There are some early failures related to production processes, flows, installation problem, soldering that is done poorly and so on. But if we want just to focus on the wear out damage mechanism that I was mentioning before, so as engineer we expect the components fail according to this mechanism. You know, they are really, yeah, they are really they have some sort of discipline, so they need to fail according to this particular damage mechanism. You know, but in reality they do what they want. So basically, there is a combination of damage mechanisms, right? And you spend a lot of time. You spend a lot of time.
All these mechanisms are competing, and you know, the
Yeah.
one that wins most often gets our attention, but oftentimes we skip the second place winner.
Yeah, and that depending on the mission profile, basically, if you have like you take some assumption the mission profile, and you have a dominated damage mechanism, which in reality is not the real one. So what I want to say, so basically, we need to this is what is really nice from the design for reliability point of view. So we need to go through all the V model, so from the requirements to design to test, yeah,
Hmm.
focusing on different damage mechanisms, but conscious of time and the time to shipment, time to market. We need also to take some well educated assumption, and be humble, regarding damage mechanisms, because it might be, that there is a combination. So this surprise is part of the life of a reliability engineer, I think. Yeah.
Well, there's a role in there for really good design guidelines. and I'm more of an electrical engineering type background, but there's similar things for mechanical. But the mechanism for ceramic or for aluminum electrolyte little basically can capacitors
Mm.
is what I typically call them, aluminum electrolyte, um, is they tend to have a dielectric breakdown. Over time they see voltage spikes or they see transients and it starts digging a hole through the dielectric and eventually it shorts it out. Or it loses the electrolyte solution. It leaks, and there's various reasons for that, and that'll occur over time. But if you increase the heat, say through a high ripple current in that circuit, it'll internally heat it, and it'll evolve off that electrolyte solution. But those are just two failure mechanisms. And they've
Yeah,
been around ever since we've had these capacitors. In many organizations, not all that I've run into, most electrical engineers understand that. And so they select components that are overrated for the details of what they're doing. So if they're doing a 5-volt trace and they need a capacitor across it, they'll get a capacitor rated for 10 volts. So they'll derate the capacitance that they need in that spot. And they'll get one that's a little bit bigger. It gives them margin. And what I find is that people will look at derating and go, oh, what's that? That just means we buy more expensive components. But if you think about what are the failure mechanisms and why we do derating, then it's exactly what you're talking about. So it's something a lot of engineering teams do very naturally. They have design guidelines, they have different criteria and standards that they're designing to. That goes a long way to account for a whole raft of different failure mechanisms.
yeah, yeah,
But the issue is that we often then focus on the new component, the brand new attachment mechanism, the brand new way to transfer this load, a new dampening system, or a brand new invention for keeping a system level when and it has a rotating element to it. Those are cool. They're exciting. They're fun to work on. But I often think of it as that those are the ones that get a lot of attention, which in a lot of cases really does need a lot of attention. Yet it should not sacrifice the value of paying attention to all the nuts and bolts and basics of making sure
yeah.
everything else is right.
Yeah, I mean, and I agree with you. So it's always so good reliability engineering is a good design, is good engineering, right? So
Right.
and good engineering start from the basics, so from designing properly what are the fundamental parts, electronics and in mechanics. Yeah, and I mean, I think reliability engineers should apply engineering approach. So basically, they can of course focus on what is expected to be the weakest link, or
Mm-hmm.
the damage mechanism with least the least investigated damage mechanism in order to be confident, that there is damage mechanism that not occur in the field, but they need also to not to be, let's say, completely drawn by the analysis of each single components in the same way, because it takes huge time. So it's
Right.
not consistent with the time the engineers have. So they need to combine this kind of component level with, let's say uh, more subsystem level and system level, and this where you say, okay, I have analyzed most of the risk, but I still might expect some surprises, right?
Mm-hmm. Mm-hmm.
In the system level, and this is, I think, the reason why the majority of the company, they cannot rely on component or, let's say, interface level testing, and they at the end they do the so-called ceremonial test, to see, even if I agree with you in terms of statistics,
Right.
it does not provide.
Yeah, some companies even call it beta testing. They hand it off to customers and say, right, we're going to give you stuff and it has other purposes. It's real use, it's in the customer's hands, how they would use it, and so on. And
Yeah.
with good beta testing people on the other end, they know that this is a part of the process and don't be upset when it fails. Report it, gather information, stuff like that. You can increase the sample size. It takes a little longer, but it gives you really real
Mhm.
world feedback. And if done well, if that kind of program's done well. Um, but yeah, the complexity of our designs, I don't think is ever going to go away. You know,
Yeah.
people keep inventing new materials, new techniques, new processes, uh, and we have different solutions for things. And as we make things smaller and lighter and less expensive, even what was once a simple device now when it becomes a miniature version of
Yeah.
it. Now it's a relatively very complex product. And again, because the ability to craft it to yeah. One last thought is you know about Moore's law, right? Where the
Yeah.
is what every I forget
Every
the
2 years, the
every two
numbers
years,
of, yeah,
yeah, number of transistors.
transistors, yeah, is a duplicate, is going by twice. Yeah.
Yeah, and now they're coming up with all kinds of other ways to just keep it going. I think we're running into the fundamental limit of that at some point here. If you really
Yeah.
can't. But the idea is that as the circuits and chips get smaller, it had effects on temperatures, on heat transfer, it had effects on electromigration, it had effects on how you design and operate a circuit board. How do you deal with all the it has a ripple effect. So if one area gets really improved, there's almost always auxiliary is I'm not sure if that's the right word, unintended consequences in the rest of your system. Um, and so I think you're exactly right. In it's good engineering. It's honest assessment of the risk and
Yeah.
laying out enough energy and effort into the areas that are going to add value. And yeah, do the whole system, see if it works. Um, we rarely at that stage have enough time or samples or anything else to do much about it. Um, but we one last thought is the companies that I've worked with that are working on what I would call a complex or complicated or either way product,
Hmm.
um, that take every opportunity to learn. So if something doesn't look right, they dig into it, find out why is it behaving that way? Is that going to be a failure the customer cares about? As opposed to unit companies that say, well, that was a software glitch. It's not, I'm not a software engineer, so I won't worry about it and not even report it. And you can
Yeah.
see what happens in an organization like that is they had the opportunity to fix things that they saw, but chose not to see them.
Yeah, I think one consequence of a complex and complicated system should not be let's test everything at system level because I don't know and don't want to know the damage mechanism at component and interface
Hmm.
level.
Yeah.
You know, this level, this is definitely something that should not be done, right? So I encourage reliability engineers to apply a good engineering approach, and digging into the damage mechanism, saying what and combining that with a systemic approach. But if the company starts saying, "Hey, this is too complicated, this is too complex, let's pack everything together at system level. If it works, everything will work." This is definitely the wrong approach to be
Yeah.
followed. Yeah.
Yeah. No, I totally agree. I don't know. So if you're listening to this, we've been chatting about these, complex or even complicated type products and different ways to approach that, or a way of approaching that for reliability. What are your thoughts? If you're a rocket scientist, you may have some takes on this, or an aircraft, or an automobile, or a drilling, exploration for or a drilling system, or whatever. It could even be a fountain pen. It's what techniques are you using? What areas that are you seeing are weaknesses? What areas do you have questions in? All of those things are fair to let us know. Get a hold of us and we'll try to help you with get an answer or find an answer to your questions. Or if you have comments and or the questions, we'll probably talk about it again in a future episode and get a little bit deeper into it. But if you can do that over at accendoreliability.com/go/SOR, and there's a couple of ways to get in touch with us. And Enrico and I and the other hosts of the show are available through LinkedIn and our About pages. So we really do look forward to hearing from you. And thanks for listening. Appreciate it so much.
Thank you. Thank you, Fred.
All right. Thanks, Enrico. We'll talk to you soon.
Bye.
Bye-bye.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.